Yes. So, good afternoon, participants. For the third session of today's third session on FDP on 3D printing and design. We have with us Dr. Mohammad Imtiaz Ahmed from IIT BHU for this session. So, I will introduce Mohammad Imtiaz Ahmed, sir, in a very short. Sir, good afternoon to you.
Good afternoon. Thank you, Dr. Yogesh.
So let me introduce in short and then we can start. Okay. So Dr. Mohammad Imtiaz Ahmed is working as an assistant professor at Department of Ceramic Engineering at IIT BHU. His research interest includes inorganic photovoltaic materials, composites, material processing, 3D printing of ceramics, etc. In a very short period of time at IIT BHU, Dr. Ahmed has completed 4 research projects as PI amounting around 79 lakhs. It may be more if I am not correct. He is actively involved in, he is actively working on 3D printing of ceramics and composite materials. Sir, I request you to kindly deliver today's session.
Okay, thank you, Dr. Yogesh, for a rather generous introduction. And I also would like to thank all the organizers for inviting me here. I am really glad to give a talk at this forum. And I see there are a lot of participants. It's irony that due to pandemic, we cannot really see all the faces and, interact the way we could have liked it. Nevertheless, yeah, we started working on this additive manufacturing at IIT BHU. Actually, Dr. Santosh, Professor Santosh, has been working on this for some time. I just joined him, and for the ceramic manufacturing. I have a lot of interest in processing of ceramics, so I will talk it from that perspective more than exactly on the additive manufacturing. There are some issues with the ceramic additive manufacturing, and those issues I will try to highlight in this talk. At the same time, I will also like to I will only concentrate on those techniques which are having more potential for ceramic materials. Okay, so before that, what I will do is I will try to prepare a background and then give you some techniques and then give you the drawbacks and issues that currently people are facing. And so till date, only few examples of successful additive manufacturing of monolithic ceramics are there. There are issues actually, and we will be talking about that. Okay, so I will share my screen, and then I will continue my talk. So here we go. If you see my screen, just say thumbs up to me. Yes, it should begin. Let me stop this. Yes. So, yeah. So can you guys see my screen now?
Yes, sir. Yes.
Okay, great. So my topic today is additive manufacturing of ceramics. I guess ceramics is not taught in many colleges. It's not very common branch. Among IITs, it's IIT BHU is the only IIT which has a ceramic discipline. I will give a little bit about. So my outline will be like this. I will talk a little bit about the applications of ceramics, what ceramics are. Many people think ceramics as traditional tiles and things like pottery or some glazed items and stuff like that. But ceramics actually is much more than that. It is there everywhere nowadays. And so I will just try to highlight some of the applications of ceramics and some properties of ceramics which are detrimental as far as the manufacturing or additive manufacturing of ceramics is concerned. Then I will be concentrating of talking about some of the AM processes which has a lot of potential as far as the ceramics are concerned and their examples. And then I will talk about issues and potentials, and then I will give you an outlook or a summary kind of a thing. Okay. So let's see. What are ceramics? Actually, ceramics by property, they are very hard, brittle, and generally insulating materials. That's what comes up. But there are examples of ceramics which conducts, like for example, zirconium diboride is one of the ceramic materials which could conduct, which is pretty much like metallic. Then you have by processing techniques, ceramics are not processed like metals. Like for example, the refining goes on in metals and then you pour it in molds and you give them a shape, or you do forming like applying forging and etc. like that. But in ceramics, you cannot do that inherently because they are very brittle materials and they are not formable. So what we do is we apply heat and pressure, and we begin normally, the processing begins with powder processing. So you powder it, that makes it flowable, and you give it a shape by adding some binders or something like that, and then you sinter it. So it has got some processing steps that needs to be done. And by exclusion, if you want to look at ceramics, if you touch anything which is not metal, which is not a semiconductor and a polymer, then it is absolutely a ceramics. Okay. So this is how sometimes you can look at it. They are generally inorganic materials. So ceramics are generally classified as oxide ceramics, nitride, borides, carbides, or silicides. You have binary compounds which contains two elements, like for example, MgO, TiC, alumina, zirconia, zirconium diboride. Then you have three elements, more than one or mixture of two compounds basically. So in this case, like for example, if I look at here, this one, it is a mixture of BaO. By reaction of these two, you can say it forms. So that's why I have classified as again a binary compound, because it's essentially a mixture of two compounds. So, and also silicates, traditional ceramics are mainly made up of lot of traditional ceramics are actually silicates, and silicates are also vast majority of the Earth's crust. Okay. So these are some examples of ceramics that I have put in. You all know these pottery stuff you see everywhere, like stoneware, porcelain, or china bone, or bone china and stuff. They are very beautiful sometimes, and people like to keep them in their houses, like dining sets and so on and so forth. These are all traditional, and sometimes they're glazed. These glazes are also very useful in terms, like it makes it non-porous. Glazed items are also used in electrical insulation, traditional insulations that you see in old or in near transformers or in electrical poles and stuff like that. They're all glazed. It makes it non-porous, so water cannot go in, and it cannot become conducting or so. And it also becomes very beautiful. Now, glasses are also part of ceramics. It's made up of silica. Primary constituent of glass is silica. And so glasses have come a long way. 20 years ago, people used to think glasses means they are something transparent, very fragile, and so on and so forth. But today, glasses have become very strong as well. Examples are your mobile phones or mobile devices. Nowadays, people are using glasses in the structural, somewhere where the compressive loading is also applied. And a lot of buildings are coming up with glasses which can be tinted, which can be given a lot of colors and so on and so forth. So glasses have come a long way these days. Then you have refractories. These are very, very critical in terms of, like, if you do not have refractories, you will not have good metal. That for sure. The reason is metals require 1500 or 1600 degrees C temperature for processing them, purifying them. And to do that, you cannot have a metal pot. The reason is they will react. Most of the metal melts or becomes very fragile, very mushy at those temperatures. So you need something which can withstand those temperatures without breaking, without yielding, and at the same time chemically inert to the processing that you do, or ingredients that you use for making slag and so on and so forth. So these refractories are actually ceramics. They are generally oxides. For most of the steel industry, we use magnesia or silica kind of stuffs for making refractory linings to the ladles or to the furnaces, blast furnaces, electrical arc furnaces, where actually processing is done for shaping the metals, okay, for metal processing. And also the glass industry also requires these refractories for processing. So ceramics is also used, and you require several shapes and sizes of these bricks, or they sometimes use monolithic refractories as well. Then you have chromite-based refractories, carbon-based refractories, which are coming nowadays. So that has also come a long way. And then you have uranium oxide, which is used in reactors. It's also ceramics. You have float glasses. You have pore-free ceramics. Now here is an example that you see in this case is a transparent ceramics. This is not glass. This is a transparent crystalline ceramics. It is sapphire actually, alumina. So when you make it 100% dense, inherently ceramics should transmit the visible light. And so these have applications in windows and domes, which has to be RER transparent. Sometimes they are used in cones of the rockets and so on and so forth. Then you have silicon nitride ceramics. There are also very high-end ceramics used in aerospace industry. Silicon nitride is also used in solar cells for anti-reflection coatings. Then you have magnetic ferrites. All these actuators or the motors, it contains some kind of a magnet. And ceramics is kind of magnetic. All magnetic ferrites comes under ceramic materials. And you have about early 1930s, 1 million ton produced annually it was. Okay. Nowadays, it is almost 1 million ton annual production of these particular class of ceramics. Then you have titanates. About more than 50% of the electroceramics actually are titanates. You have optical fibers nowadays used for transmitting data. That also is a ceramic material. So ceramics is kind of everywhere nowadays. And then you have cooktops. Actually, people were looking for transparent, hard material which could be applied for ballistic missiles, and ended up getting what is known as glass ceramics. Okay. And so cooktops nowadays are coming. They're very tough, very hard. You can actually put everything on it, cook it, heat them and cool down. Nothing will happen. They're not fragile at all. They look transparent, but they're not fragile. Then you have toughened ceramics. Generally, zirconia is used there. There are some examples where toughened ceramics are used. So K1C up to 12 MPa root meter. Actually, it should be root meter here. There is a mistake here. It should be MPa root meter. All right. So you have up to that. It is not close to metals. Metals generally have much higher fracture toughness, but this is good enough for this kind of application where more loading is compressive rather than tensile. Then you have biomaterials, a large class of biomaterials. Nowadays, there is a separate class of material known as bioglasses. So these are very inert materials, some of them like hydroxyapatites and stuff. Nowadays, it's very, very popular bioceramic material. Then you have fuel cells. Almost everything of the solid oxide fuel cells is made up of ceramics. Then you have high temperature superconductors. They are also ceramics. So ceramics is everywhere. That's what I would say. So, but the problem with the ceramics is this, or the advantage of the ceramics is this. Both comes hand in hand. One, melting point. Like, for example, if you look at alumina, it has 2000 degrees C melting point. That means if you want to pour alumina somewhere or cast it, you cannot do that. you have to go to a temperature where it is more than 2000 degrees C, 2100, 2200 degrees C. Now, those, it will become a nuisance for processing. The reason is for that you need heating elements. And these heating elements are either carbon or zirconia. They can give you this kind of a temperature. They can withstand that temperature. But now these gets oxidized also. To protect the heating element, you need a inert environment. So now you maintain the heating element becomes another problem for you. So that's the reason. And also they are very tough. If you pour them from the melt, they solidify, they crack. The reason is they cannot take thermal gradient. So these are the reasons. So now if you see the melting points, copper or nickel or iron, they are less than 1500 degrees C most of the times. Aluminum, if you look at it, is about 660. But look at these ceramics, which are generally used. These are most used ceramics, and they have very high temperature required for melting. And also the loop hardness, you can see it's very hard material. It's very brittle, very hard. Now, if you look at some specific strength of ceramics, they actually inherently are very strong. The reason is their bonding is strong, but they cannot resist the and the presence of a flaw. They cannot resist tensile loading. They eventually break. And I will talk about it. Why do they break? But if you look at the ceramic materials, they are very close to your traditional metals and alloys. And also the density is lower. If you look at one more advantage of ceramic material is that your density is actually lower, but your strength is almost on the same segment. But there are other problems with this that we will talk. Now, if you look at here, the temperature at which they can serve you, the ceramics can actually serve you at temperatures greater than 1000 degrees C. You can see the arrow here. And most of the metals will not be able to serve you beyond 600 degrees C. There are some specialized materials like in Cornell and all, they can go up to 800 degrees C without oxidizing, or they can resist oxidation to some extent, but not for very long, in the sense you cannot apply it for continuously above 800 degrees C. But ceramics can regularly be done, can be used at temperatures higher than 1000 degrees C very easily. And there are materials like, for example, if you go to spacecrafts, in those spacecrafts, you can see there are certain things which requires temperature resistance up to maybe 2000 degrees C, 2500 degrees C. Those places also, these class of ceramic materials are used. They are having less density, and they can withstand very high temperature. You can see that. And that's one of the reasons why people are so much interested in ceramic materials. But this is the problem with the ceramic material, the fracture toughness. The fracture toughness, if you look at for ceramic materials, is rather low. What is fracture toughness? Fracture toughness is the resistance to failure in presence of a flaw, you can say. Now, if there are some small flaws everywhere, when you process a material, you eventually heat them, cool them down, sometimes you form them, and so on and so forth. And as a result, some flaw remains. Sometimes it's small flaws in microns or submicrons or so on and so forth. But in case of a metal, their fracture toughness is high. You can see that they are greater than 10. And most of the stainless steel or high entropy alloys, copper alloys, they are close to maybe 60 to 100 actually, if you look at this range, greater than 100 sometimes. But if you look at the ceramics, this is log scale. So if you look at the ceramics, you have hardly 10. This is where alumina is about 3 to 4 MPa root meter. And if you look at zirconia, toughened zirconia, which is probably one of the toughest ceramic materials, it has got 12, and nobody has produced more tougher than that material, that ceramic material. So this is the problem with the ceramic material. And now if you are heating it or processing it, you eventually end up with cracks. And that's the reason why, even though they are very strong materials, but in processed product, if you apply a load, will fail. and fail in a brittle manner. And the failure will be very much unpredictable. So that's the problem with the ceramics. So another problem with it is the thermal shock resistance. If you look at this TSR, thermal shock resistance, if you look at here, it depends on the fracture strength. If you are hard materials having higher fracture strength, okay, and at the same time you have very low thermal conductivity. And that's the problem. Ceramic materials, if you look at, generally they will be very steep. So they are very good E value, high E value. That means it has got low this thing. At the same time, your thermal conductivity is small. So again, it is small and it is again lower. And that's why. So here is an example of a missile cone which was fitted in an aircraft, and the aircraft went up, came down. Because of this, up and down movement, it generally the outer portion gets heated up because of the resistance of the air and some particles landing in the air. They rub on it and it gets heated up. So generally, aircraft goes up to a temperature of 600 degrees C if it is flying. And fighter aircraft can go up to 600 degrees C actually. So when it cools down, when it comes down and suddenly it lands back in the airstrip, it cracks. And that's a very big problem with the sapphire kind of or MgO based MgO alumina kind of windows. So people are looking for these windows as well that can be toughened or not. But that's the question. So these are the issues. Now, if you look at the additive manufacturing, I'm sure you have already been introduced to additive manufacturing per se, and I will not repeat it. Only thing I wanted to say at this point is the parts having arbitrary geometry can actually be produced by this additive manufacturing without producing much waste. That's very important part, without producing much waste. And that's why many people keeps this additive manufacturing in a green manufacturing segment. Okay, and you can also get sometimes semi-finished, and in case of ceramics, you almost always get semi-finished product. I will tell you why. Now, why people are looking at additive manufacturing, especially as a ceramist, why I am looking at it? Because generally ceramic materials, ceramic products are critical products which are not used as a big structural elements, but many times these are miniature small elements which has to be fitted in certain places, which sometimes are loaded also. Okay, so they have very complex and geometries sometimes, and additive manufacturing enables that without need of machining. The machinability of ceramic materials is very poor. Although there are examples of machinable ceramics, but generally they cannot be machined because they are very hard, and you cannot make a tool which can actually cut through your hard material without destroying it. So itself basically. So the control of dimension is also required. Then you sometimes need porous bodies. So the question is, because porosity is a functional element in many cases. Like for example, if you're talking about bones, in human bones, the porosity is a functional element, functional property, because it requires, sometimes you're talking about filters. So the question is, can we engineer pores? That's the question. So additive manufacturing opens up that gate as well, that kind of a venue as well, where it might become possible if you can control the resolution to control the pores. So we will look at that, and it is suitable for fine and fragile structures. Again, you are going bottom up approach, so you can also make very fragile element from by building on it rather than cutting it through. Okay, but having said that, there are very few examples of dense ceramics being produced by this particular technology. The reasons are many. I will come to that, but before that, I want to give you a summary of what is going on as far as the ceramic materials are concerned in the field of additive manufacturing. So there are some indirect methods. I guess you all know that there are layer by layer deposition is possible to build cross sections, and you just model the cross section and build one by one and build the height. That's one way. Another way is you complete the separate parts and then you assemble it, or you create a green body. You create a green body which is applicable to ceramics only, or most of the cases it's applicable to ceramics. The reason being ceramics cannot be formed. So what you do is you make a green body with a binder, control the shape, and then sinter it. The problem is, due to sintering and densification, your size will change. And another complexity comes when you have elements of different thicknesses and different cross-sectional areas. The reason is the shrinkage will not be uniform in all these different thicknesses. And that poses a lot of problem, how to predict the thickness. So if you do not know the end, how much shrinkage it is going to have in particular element, you cannot design a product, semi-finished product, and sinter it to get it without processing it further. So that's another problem. And another nuisance is the binder burnout and densification step. So, and other ways to deposit the powder and directly get the material by sintering it in situ. So that's called, that's one more process that we will discuss. And then in situ densification has its own problems. The reason is you need to take the powders to melting temperature so that they can fuse together. But that adds to thermal gradient. The upper portion, which has been processed earlier, would have been cooled, and you are heating the top portion, so that creates a gradient. And we have seen just now TRS, TSR of ceramics is not good. So it will not withstand much, and it will eventually end up getting cracks. Once it has cracks, it becomes very fragile. Although ceramics are hard, but in presence of cracks, since the K1C or the fracture toughness of ceramic materials are low, it will be very difficult for it to sustain any loading, and it will break eventually. And so that's another problem. Now, you can also talk in terms of free form. That means how to form a solid. You can either form by adding pointwise, and that's how we do in case of powder processing. You do additive manufacturing from a powder. Do not process the powder much. Add just some binder and build the powder one over another, a layer over layer. So when you build with powder, we call it pointwise buildup. And either you can draw a filament and then deposit that filament. That's line kind of a process. So you are building the thing line by line by controlling the dimension of the line, dimension and the thickness of the line. And another way to look at it is building plane by plane. That means what you do is you have one particular sheet, you cut it at a cross section as a function of height, and you keep cutting that as a function of height and maintain the cross section and build the part. Okay, so that can be done, and all these three can be automized by the help of a computer. Okay, so now the product characteristics. So what kind of characteristics we will look at as far as the product is concerned? Now, you can have a product made up of very small volumes, but joining together in 3 dimensions to give you a larger product. And these small dense elements are called studs sometimes. Okay? Then you can have volume, like for example, a piece of brick. It is monolithic. So you have a maybe for 10 mm, 20 mm, or maybe a few centimeters, few inches to few millimeters, few meters, single piece of a product which is dense. Then you can have micro porous product. That means it looks like dense, but it can have porosity in it. And those porosity can be macro porosity. That means you can measure it you can see it from your eyes, or it could be greater than 1 millimeter. Okay. Or you can have micro size. That means less than micron. So it is in micron or even nanopores. So you can look at porosity. Then you have product dimensions. How big the product is. It can be all the three. Okay, any of these top three, but it can be small or it can be big. So that also needs to be considered when you are looking at what kind of processing you are going to choose, post processing and strategy you are looking at. Then what kind of surface quality you require. Okay, and then the precision. So like for example, I have a gear here on the right side of the screen in the middle part. How precisely you can reproduce that teeth and the corners, that will decide the functionality of that particular element. So that becomes another important parameter that we need to look at. And the cost, which is probably the top, because that's going to hurt your pocket. So the cost can be divided into two. One, how much feed stock you need to prepare as far as ceramics, because ceramics require a lot of feed stock, and whatever you feed, you get the result. So feed stock has to be reasonable and also not so costly to prepare. And then after processing, what kind of post-processing you need to do, that also determines your cost, because I said you require sintering for the ceramics to become stronger, right? To make it denser, to fuse them together. Now, sintering requires temperature and time, and both are very, very costly. So it is going to add to any processing that you do is going to add to the cost. So that's also a very important point that has to be kept in mind. Now, I will not go into all the processes, but I will just talk about broader processes, which can, and all the other processes are probably some modification, or they are some modifications of these few technologies. And also these technologies are more having more potential as far as the ceramics is concerned. So that's the reason why I have chosen a few of them. And first one I will talk about will be the powder-based 3D printing. And you have selective laser sintering. I will not call melting. The reason is I don't want to call melting as far as the sintering is concerned. If the material is able to fuse, then I will consider it to be processed. Then you have, it can be powder-based or slurry-based. You can have a slurry or you can have powder and then build it. And then stereolithography, I will talk about it a little bit. And then laminated object manufacturing. I may not talk about this. Instead, I will talk the other one, the filament deposition method, which is nothing but the excuse me, a modification of extrusion process. So yeah, so I will talk about fused deposition modeling, and then I will not talk about inkjet or other mold making processes. They are not very successful as far as ceramics is concerned. Inkjet of late has become a little bit successful in the sense but these are generally applied to very, very small elements, which can be printed micron sized or less, sometimes some microns also, where you need a lot of precision, but you cannot make big products out of this. So I will just skip that part. Now, powder-based 3D printing that we talk about, which is applicable to ceramic materials, is a schematic I have put in this particular slide. And I'm pretty sure you have seen this before. So what you actually do is you have a base. Yeah, so you have a base, and then you have a small, initially this particular thing is actually high up here, and this particular thing is printed. So what you do is you just supply the powder from here and put it a layer on this, and this is binder head, which is just like, you know, a XY movement, and it works exactly very similar to like printers work. And this particular head is computer controlled. So if you have, let's say, this is the bed, and if you want to produce something like that, you just put a powder on it everywhere, one layer of powder, and then you deposit the binder over this powder, and then you build another layer of powder on it, so that the layer which is depositing over this binder will stick to it, and rest of the powder will not stick to it. And then you will again put binder on it, and you keep on building it. At the end of it, you remove these loose powders out here, and you get this particular product. This is your product. Now, this has got a binder in it and some plasticizer or whatever. Generally, it is not having plasticizer because we are not. So it contains binder and some other aids, powder flow aids or whatever, which makes the powder better to, you know, well spread and so on and so forth. And then now what you need to do with this product is to sinter it, because it's not very strong. It's just some polymer binder that you have added to the powder. So you need to, first thing is to remove the organic binder and sinter it. Okay. So the binder generally is used is organic binder, generally dissolved in water or some kind of a solvent which should not react with the powder. Now, you can also have some reactive liquid. Sometimes this stage actually is heated also a little bit. You can have a little bit of a heating on this stage, which can make it, you know, sometimes activates the binder to bind it better. Now, binder removal and then sintering, these are two steps that has to follow. And because of that, when you remove the binder, it leaves a lot of porosity in the product. And you need to stay for very, very long time to close up all those porosities. As a result, generally, the product, if you are very careful, you will still have at least 20% porosity in the product. Now, porosity can be controlled, yes, but only those porosities which at this point, at this current state of technology, is you can control microporosity, but not microporosity. You cannot print this porosity, but bigger pores, yes, you can print. So sometimes this is beneficial, and for biomaterials, this is very, very, very beneficial, and people are actually trying to use this there. In fact, a modification of this process is being projected as one of the top contenders as far as the mainstreaming of ceramic 3D printing is concerned. Now, powder processing becomes very important here. So if you look at, if you have very small particles, which are, say, in terms of few 100 microns or even sub-microns, a few sub-nanometer, or in few 100 nanometers or so, if it is like that. And on the other end, you have very large micro or micron, several micron size powder. Now, packing you cannot get by using very fine powder or very coarse powder. In order to get the powder packing good, you need to come somewhere. That means you have to mix. Generally, a bimodal powder size is more beneficial or is chosen. And by doing that, you can increase the packing density at least by 30%. And that's the reason why people do not use monomodal powders, but they use bimodal powders. They have two different size distributions, which are at two ends, or somewhere like some of them are sub-microns, some of them are few microns, and then you pack them together, and that gives you better packing density like this one. This is what is our goal. Now, if you look at the powder size versus thickness, how much thick? Thickness means you have one layer, you build another layer on it, This is called thickness, T. So the thickness here, this part gives you thickness. And this is the size of the powder. 240 grit means 53 micron, the granule size of the powder. Now, if you look at either of these smaller and smaller powders and thicknesses, different thicknesses you build, you cannot go to very high density. Your density can be about 90, 92, 93%. But if you mix these powders, at least in bimodal mode, mixed powder. So they are not single size, but they are having a mixture of sizes, mixed particle sizes. In that case, almost in all cases, here you can build large layers or smaller layers also, thinner layers, that means. And you can see you achieve about 97% dense product. That's important. So when you are processing the feed for the additive manufacturing of ceramic materials, choice of powder sizes and their distribution is also important, and how much thick layer you are preparing each time. So thinner the layer you make, costly the product will become. So, but then with thinner layers, you can achieve greater densities. You can see thinner layers gives you better densities, and thicker layers with larger particle sizes do not give you good density. So that's an important point. So this has to be kept in mind. Apart from that, flowability of the powder also comes into picture. Now, densification part. Once you have made your product, you need to make them dense. And that's an important point. And in order to make them dense, you need to sinter them. But if you want to lower the cost, you need good sinterability. You need less time and less temperature for sintering. So in order to lower the melting point, sometimes you add some additives or some other compounds which reacts and forms some kind of eutectic or some kind of a low melting compound with the parent material, and gives you a flowing liquid or a fusing liquid or a mushy zone somewhere between the grains or somewhere between the particles, and which allows the particle to resettle itself and pack better. And it also acts as a bond for whole thing to become dense. So zinc oxide or silica is sometimes added to tricalcium phosphate, and people have achieved about 95% relative density. Relative density means theoretically the compound, if it is 100% dense, it should be having certain density, and the density of the material that you have prepared is compared with that theoretical density. And that's how people talk about relative density. And then calcium trisilicate or calcium silicate compounds are added for also known as wollastonite for hydroxyapatite. And people have achieved about 97% relative density in hydroxyapatite using that sintering aid. This is the example how the shrinkage happens. You can see this is 10 millimeter. Both are having same scale, and you see this is the green body. It looks rough and it looks really large. And when you sinter it, after sintering, it shrinks. Now, alumina preforms, if you make and you have some porosity, generally what they do is either you can infiltrate with aluminum. Many people make, and it becomes a composite, or sometimes they infiltrate with copper. So close these pores, they pack them. And one such example, it was achieved about 236 MPa as a strength, flexural strength, and K1C, you can see for traditional alumina, K1C is about 3 to 4, but in this case, it had greater K1C value, that means fracture toughness value. And then there are examples of reaction bonded silicon carbide being produced by this process. What people do is they add the powders together, because reaction bonding, what it does is You apply silicon carbide with some silicon or some yeah, and then what you do is you heat them. Okay, so when you heat them in presence of some carbon forming material, it actually reacts and forms silicon carbide, and silicon actually melts. Okay, and it bonds these silicon carbide particles together, and also later on, some part gets carbide forms silicon carbide also. So this is silicon actually, not silicone. Okay. So infiltrated liquid with silicone, and if you pyrolyze it at 1000 degrees C, you can get, and then whatever pores you have, you can infiltrate with the silicon. The melting point of silicon is about 1400 degrees C, so you can infiltrate it into it and get a pretty dense silicon carbide. Sometimes for densification, you apply warm isostatic pressing, but before that, you have to remove the binders. And by applying isostatic pressing, you can attain greater density. One example of alumina with magnesia doping, people have achieved about 99% density with a flexural strength of about 325 megapascals. But only problem with this particular approach is that it cannot be applied to complex geometries. Now, we will talk a little bit about the selective laser sintering. So this is very similar to what we have seen earlier. Only thing is that instead of applying a powder, applying a binder, we have binder already added to this powder. So powder bed contains binder. And the binder is such that polymerizes on UV exposure. So you spread the powder, you again have a cat drying, and you have a reflecting mirror which scans over the powder, and wherever this laser source or the laser beam scans on the powder, the polymer which is already added to the binder already added to the powder gets cured. And oh, I'm sorry, this is laser sintering I'm talking about. Okay. So in this case, we do not add any binder. I'm sorry. Okay. I was thinking something else. Okay. So we do not add any binder in it. Okay. Sometimes we add binders, but I will talk about it a little later. In this case, what we do is we have powders, and we apply laser and fuse them together. That's what we do. So instead of pouring the liquid binder, we fuse the material by using a laser source. Okay, that's why it is called selective laser sintering. Okay, so it does not need, the best part of this particular method is it does not need any feed preparation. You can have any kind of powder and just sinter it directly. But the problem is it generally results into porous product. I will tell you why. So you do melting or sintering directly. The problem is that if you have built this layer already, the lower layer is cold or just warm, and here you have added a powder which is above that. You are applying a low this thing, and it fuses. Now the temperature here is high, and there's a gradient between this, and so you generally get a cracking here. So it is very difficult to form crack-free ceramics by this method. Sometimes, in order to aid this people add metals or some inorganic binder. But then if you add these things or inorganic binders or something, you again have the nuisance of removal of the binders. And as a result, you generally get what happens is if you have powders and you apply this thing and you sinter this part, this gets sintered and this gets sintered. Sometimes this inner part is not sintered well. And as a result, when you keep building it up, you will have these pores which cannot be filled by anything, and it remains porous. So as a result, the green strength is not. As a result, the strength of the final product is not good, and because of that, also there are generally rough surfaces. I will show you some examples of it. Here is some good examples, in the sense some success stories I want to share, and one of them is the bioglass scaffold. People have produced bioglass scaffolds with 50% porosity. Why we use selective laser sintering? Because the reason is glasses are relatively easy to form, and selective laser sintering inherently results into porous material. And for many of the bio applications, you actually require porous products, and that's why one of the success stories. And then we have another example of again the silicon carbide with polysilane, polyhexane basically. So it is silicon carbide composite kind of a thing, and you later on infiltrate with silicon. Very similar to what we do in case of 3D 3D printing of powder 3D printing. Very similar to that. Here we work. Only thing is that here we do in situ reaction bonding. In the sense, the powder is there, and when you apply laser, it gets reaction bonded by silicon. Silicon carbide gets reaction bonded, and then you infiltrate with pyrolyze and infiltrate with silicon. And so this is another. There was another report which is actually a success story, I should say. Now densification. So laser, if you are putting laser there, sometimes the temperature will not be high, and so as a result, what happens is the temperature is high generally, but what happens is if this region is getting heated up, and then you end up having some pores inside, which is not really getting dense much. So what people do is, in order to reduce the melting temperature of the powder, which will make it more effective as far as the sintering is concerned, you can add low melting elements in it, low melting components in it. Like, for example, in case of zirconia, the melting point is about 2700 degrees. 2700 degrees. Now, it forms a eutectic which can melt at 1860. Now, if you add about 10% alumina in zirconia, what you will see is, although large part will not will still be solid, but a small fraction. So if you want to find out if it is 10% alumina, at around 1800 degrees C itself, you will have this much of liquid, about 8 to 10% liquid you will have. And that will be enough for you to densify or bond the grains together. And so people use low melting eutectics, which helps, or liquid phase sintering, And so people have been able to produce zirconia alumina with 500 MPa strength. And also to prevent the cracking, sometimes what they do is another laser is used to preheat the bottom part from other side. Or sometimes people use some kind of people do this process in some kind of a heating arrangement. So whole product is being heated while you are doing the laser sintering. So that reduces the chances of crack. And the beauty of this process is you do not require any post-processing. Where is it is gone? Okay. Yeah. So you do not require any post-processing in this case. Now for SLS, there are some sacrificial binders that sometimes which is used, and here is a list of it. Excuse me. I do not want to go into that. But yes, you can apply some kind of, sometimes waxes are used to give them some reasonable strength before you actually laser sinter it. It is added with the powder generally. Now, stereolithography is another technique, and in this case, actually, people use the UV laser. UV. This is UV, not very high power laser to really to melt it, but it is very much like that, except that you use only UV in here, and you add polymer with the powder, okay, resin, and as a result, what happens? This example is actually from a polymer. So in this case, we have powder with polymer. It's a powder bed with some polymer in it, and this is the elevator. You keep on scanning the powder, and when you scan the powder, the binder actually melts and it binds the powder together. So wherever the laser UV falls, it binds, and a layer actually forms. Cross section forms, and then you lower it a little bit, spread the powder again, and then spread the powder again all over, and then again scan it on the cross section. So you get any kind of a shape and keep lowering the stage at the same time. And so that gives you photopolymerization. And as a result, you form a, but this is a green product. You will end up with a green product that has to be cured. So, so how much curing is possible? So this is an example. There's a relationship that has been developed by several researchers. This form was different. Recently, this form has changed. Now, if your laser, this is your UV, and this is your powder bed. This is your powder bed. So if you shine the laser on it, the depth which the powder can be cured, or the resin added powder can be cured, is CD, and CD is given by the scattering efficiency of powder particles. Because you're shining the light, so the powder particles will scatter some of the lights, which will not be used to cure. So if the scattering is high, your curing will be low. The curing depth will be low. It will not allow it to go deeper. And if the powder's particle size is bigger, larger, then what happens is, it is not absolutely true. The reason is we have a certain limit, but generally the powder size we use, which is close to in micron sizes, this is true. And so, and your laser power actually you are using here, and the power density required for the polymerization to happen. So this is the relationship. N naught is nothing but the refractive index of your media, and delta N naught is the refractive index of your feed material here. This part versus this part. So this is delta N. This part minus this part. So how much refraction? Excuse me. How much refraction is happening will also define how much deeper you can go. Similarly, curing width given by this, how much wider we can cure from one particular beam of certain size is given by this. Again, the EMA is nothing but the laser power, and EC is the curing power required for curing the polymer. And W naught is nothing but the half width of the laser beam. So you can actually know how much, by knowing your feed better, you know how much thickness you can build each time. If you build thicknesses greater than CD, you will have lamellas, which will have uncured zones between the lamellas, and that will be fragile. So your green strength will not be great. So we should always keep the layer, built up layer that we built in each each scan, it should be less than CD so that we can actually build a stronger green product. Typically, the CD is between micron, 50 to 500 microns, half a millimeter. It is possible to go up to that point. So when you have that kind of a system, you can only add about 50 to 60% or sometimes 40 to 50% ceramic particles, and rest will be photo initiator and additives. Because these photo initiators allows the polymerization to happen. They begin the reaction by exposure, and that's why it's called photo initiator. And since this is just built on layer-wise polymerization, a very freestanding structure with very thin support will not withstand, and that's why it's generally fragile. So generally people build well-supported structures by this process. And good part of this process is that since we have already added some polymers and the distance between particles are large, the reason is we have added about 40 to 50% binders and photo initiators and other additives and stuff like that. We can use all fine particles in this case. The advantage is that when you use fine particles, very fine particles as green product, after the removal of binder, when these fine particles comes in contact, your sintering will be very fast. So for smaller particles, faster sintering can happen. And that's the reason why people tend to use smaller particles. There are other disadvantages of the smaller particles that we will talk. But with small particles, and if you are building elemental structures like studs, which are not very thick, you can actually go up to 99% densification by lithography and sintering. That you have to use fine particles. Two success stories I will show you here. One of them is here. If you want to produce glass, fused silica glass, intricate structure like this that is shown here, it starts with ultraviolet monolayer, curable monolayer, which can be cured by ultraviolet. One of the examples is HEMA, and then you add these nanoparticles into it, add some photo initiator if required, and then make a slurry. And that slurry you build this kind of a structure from the slurry by exposing it to ultraviolet light. Okay. Like in this case, the ultraviolet light is being shined from the bottom, and your station is going up. So it is stuck to the station or the stage, and the stage is going up. It is building up slowly the layer. So bottom layer is built by the stereolithography. And you get a freestanding, this kind of green body, which was debinded and sintered at 1300 degrees C, and you can get beautiful structures like that. And the same group has been able to produce nearly 100% dense. The reason for the glasses can be made 100% dense because they becomes viscous, you know. So these are some examples of so many complex shapes that that particular group at Karlsruhe Institute of Technology were able to build from using stereolithography. Another example is polymer dried ceramics. In polymer dried ceramics, generally is used to produce silica-based products. So generally, silanes or silazines or similar kind of polymers are used, which can be made flexible pre-ceramic, which you can form and then later on pyrolyze it. So forming becomes easy if you have a pre-ceramics, polymerized pre-ceramics. So what they did was they took a silane or a mixture of silazanes and silicosanes, and they added the UV curable and photo initiator, And in the bath of this resin bath, they inscribed the structure they wanted to produce. And then they had, when you inscribe the structure, these photo initiators and the monomer will connect together and give you a three-dimensional network, which can withstand on its own. It's kind of a polymer. Now, this is called pre-ceramic polymer, which contains a lot of silicon oxide, silicon carbide, and silicon nitride. You can go by the mixture of it. You will produce silicon oxy nitrocarbide, nitrocarbide, or if you take only two, you get silicon oxynitride. If you take these two, you can get silicon nitrocarbide, and if you take only this one, you get silica. If you take only this one, silicon carbide, and so on. It's a very this thing, but generally people take mixture, either of two polymers mixed, and you get a pre-ceramic polymer, which when you pyrolyze, you get a ceramic product, which is either silicon carbide or silicon oxycarbide. Okay, and so this is one other example that people have been able to produce complex shapes, although very small, you can see from the picture, but it is possible to utilize stereolithography. So stereolithography is one of the important processing methods. Now, fused deposition modeling is another processing method. It's nothing but extension of extrusion. So what we do is, in extrusion, we have a cylinder and a piston here and a nozzle. So the ceramic slurry is kept inside, and you apply the pressure. It extrudes through the nozzle. Generally, long bar kind of products can be produced, or wire kind of products. So similar slurry is actually prepared and extruded through a nozzle here, and you can actually build layers on it, inscribe on the surface, and you can control the XY table on which you are depositing the product, and you can make any shape you want. Generally, rheology of the paste plays a very important role. The reason is it requires thixotropy. That means when you apply the load, the slurry should share itself, should readily share. At the same time, when you remove the load, that means when it's extruded out and deposited, it should stand on its own. And then if you keep on building a layer wise, larger layers. So if you're building larger layers, let's say this is a hollow product, so you are depositing larger layers, it should withstand this load also. So you need certain viscosity and certain shear rate with certain loading. Yeah. Any question? Yes, somebody is trying to speak. Okay.
Good afternoon, Professor.
Yeah.
This is Dr. Balakrishnan from M. Kumarasamy College of Engineering, Karur, Tamil Nadu.
Yeah.
Actually, I have some questions, Professor.
Yeah.
How effective the bond strength between layer by layer? Since the ceramics offer very less ductility during its solidification.
Yes. So if I understand correctly, your question is, how effective is this layer by layer forming is?
Yes, yes.
Yes. So that's the problem with the ceramics. There is no large product yet, except some traditional materials. All that I have showed you were small products or studs, which are larger products built from smaller studs, because you cannot or some monolithic brick kind of a structure, that one of them I showed you, which was again few millimeters or centimeters. So I will come to the problems after this particular segment, and then we can take up the questions. Because I do not know, I am telling the same thing, what you are saying. Your comment is that fusing them together is difficult.
Yes, sir.
Sir,
yeah.
Sir, we can take questions after your presentation is over.
Okay, sir. Okay.
Yeah.
All right.
Yeah. Please share your PDF file. Open your PDF file so that it is visible.
So the typical feed viscosity that we need in the powder or the slurry feed is about 100 Pascal seconds, and generally shear rate of 100 per second is good enough. Generally, people add different type of binders. Dextron is also one of them that can be actually used, or acrylite kind of binders are generally used, which is also used for extrusion. But acrylites becomes very sometimes it gives you very high viscosity. In order to take care of that, sometimes people add acetic acid or something which actually breaks some of these bonds and makes it slightly flowable. So by controlling these several components, you can actually get this kind of numbers that is needed for your. And so it depends on the nozzle size. If you make the size larger, feed becomes easier to make, but the problem is the resolution. So you have to somewhere compromise on it. Yeah. So typical nozzle sizes are actually, this is actually 1 mm, 200 microns. Recently, Professor Santosh have ordered one with 2 millimeters, and he has asked me to make a feed for it. I don't know. I am still working on it. I don't know how easy it will be, but yeah. So you have to look at those things. Generally, we do not load more than 60% particles in the feed in this case. And the filament sizes, it depends on surface finish also on the filament sizes, and the features with detail that you can print is tens of microns to millimeter. That's the problem, because you already have a strand coming out and you cannot thin down the strand. If you thin down the strand too much, the strand will break and your product will not be good. At the same time, if you make the strand very thick, your detail will not be produced. So generally, the details of in tens of microns, it is possible. MMs are easier actually. So, and in order to achieve the densification, like for example, if I am using more thick strands, then this portion will be empty. Okay, I can fill it by smaller strands. So by using two nozzles, one with thinner strand, another one with thicker strand, you can actually fill up the strands in between. Like if I deposit one thinner one here, and then before depositing the next layer, I can make it a little bit more denser. Okay, so generally these are, people say that these are suitable for infiltrated mulites, or you can also do aluminum metal infiltration in alumina or maybe silica. By doing that, you can fill up these gaps, and that increases the fracture toughness and the strength at the same time. But you can only do if it does not affect the functionality of your product. Now, the success story is that people like Miranda et al., they have been able to produce hydroxyapatite with 15% microporosity, which is needed for that kind of applications, And bioclass scaffolds also has been produced with 60% dense. So these are two examples. Both are from biomaterials. Strength depends on the direction. If you are doing this kind of stranding, then naturally the strength in this direction is going to be greater compared to the lateral direction, and that's why people go for perpendicular or several kind of angles to make it more isotropic. But generally, you can see the numbers, it's much less stronger in the lateral direction. Now, coming to the feedstock, this is very important part, but it looks very busy here. I will not ask you to read everything, but only thing I want to point out is that when you do powder processing, you can use finer particles. And in case of the SLM, you can use very fine particles also. And if you want to make some kind of paste, then yes. Now, viscosity, this rheology comes into picture. And you have to control the rheology of the paste in order to get whatever you want. So that's very important point, and lot of scope. There's a lot of scope for rheological studies as far as the paste or the slurry is concerned, in terms of how much resolution you can get and how better you can print. So just I wanted to put for this point, and then we'll talk about some issues that is being faced. Now, the properties of any material depends on the microstructure. We talked about, make a product and densify it, but what about the microstructure? Will we be getting the same microstructure as we get in case of conventional powder consolidation and sintering process? That's one question. Because when you are doing the laser melting or anything you are doing, then you have the binders in between that has to be removed, and a lot of binder is there, and the powder has to come closer. If you have more than one components, will they be able to fuse with those pores, presence of those pores or the gaps in between? So how effective it will be in terms of producing the microstructure which we need? That's one question. Now, design the sintering schedule, because the conventional sintering schedule may not work. In case of conventional sintering, you use powders which do not have so much of binder. Then you consolidate them by several methods, like either isostatic pressing, or sometimes use hot press and other processes. But in complex shapes, you cannot use those things. You have to sinter it freestanding. And so whether you will be getting with the same sintering schedule is applicable there or not is another question, because you have a lot of binders. So again, designing and looking at the sintering schedule has to be, and then for effective sintering, you need equidistant particles, you need good flowability so that you get no density gradient. Sometimes if your flowability is not good, some complex shapes will give you less packing versus the more open shape. As a result, when you hit them, it is going to crack anyway because of the differential shrinkage that will come up, that will happen. So, but if you want to use smaller, but then effective sintering is possible with fine powders. As soon as you add fine powders, you have problems of flowability. They tend to flock. Okay, they tend to charge, because if you make a smaller particle, surface becomes more important. And then you need to you require slurry formation in those cases. So for fine powders, either you go by the 3DP or use slurries, plasticizers. Now, removal of these plasticizers or slurries again becomes a nuisance. So generally, in SL method, you can utilize to some extent lower than 100 nanometer particles, but again, it's a problem. People have shown this can be done, but I'm not sure. Now, parameter optimization is very important to get the microstructure. That's what I just said in the last slide. Now, you need to optimize flowability of the powder, wettability of the powder, and how much binder area you have. You can make a product, but can you optimize it? Can you make it better further? That's the question. And what kind of surface characteristics is needed? Because that again will depend on your particle spread, your packing, how well you are able to pack, and then what is your sintering schedule, and so on and so forth. And less than 500 micron size spores you cannot print. At this point, maybe in future it's possible with the development of better technology. Now the sintering schedule. Generally, sintering schedule looks like that. This is one typical sintering schedule in which you first preheat the material to some extent where the binder can be removed. Here, you remove binder. Remove binder. And then you heat it further. Once the binder is removed, you heat it further. And in that, you start getting the large shrinkage. That means the powder comes together and then they start fusing. Sometimes they form new phases. Sometimes there is a phase transformation. So all those things has to be attended to. Otherwise, if there is a phase transformation, your material can crack. It can deform due to volume changes. So designing of sintering schedule has to be done for your product. That's a very important issue. Conventional sintering generally can go up to a very high temperature. It has to hold it at very longer time, sometimes days. It's a very energy extensive, and densification is never greater than 95 to 98%. And since we are eating it for so long, you get a lot of grain growth. So grains become very large, and sometimes they are not desirable. And if you want to keep the grains smaller, which is generally in many cases desirable as far as the mechanical properties are concerned, you cannot get to these densities. So there are alternate methods to get it. So I will just give one example here. If you are at lower temperature, let's say for example 1500 degrees C, you have maybe so this curve actually gives you So this curve actually gives you, this is actually for let's say if you require 400 kilojoule activation energy for the sintering to happen per mole, then, or let's say the example of 500. So if at 500, if you want to have a sintering rate, which is here, okay, let's say about maybe close to, we can say 40. Now, if I increase this temperature by 1900 degrees, my sintering rate for same activation barrier for the same material will become this much. So just 300 or 400 degrees Celsius or 1500 if I'm here somewhere, 100 times. Now this is 10 to the power 4 times. That means I have, or 10 to the power 4.5 times, I mean. So that means about 3 orders of change or 2 orders of a change just due to this 400 degrees change. So if you increase the temperature, your sintering rate becomes faster. At the same time, your grain growth is higher. So what you can achieve by heating at 1 hour, heating for 1 hour at 1450, you can achieve the same thing by heating at 1900 degrees C in 4 seconds. Now, if you can sinter it at 4 seconds, the grain growth will not happen because grain growth requires mass transport. And so that will not be effective. Only fusion will happen. Quick fusion at the grain boundaries will happen and no grain growth will happen. So one way to suddenly increase the temperature is by using field assisted sintering. Or sometimes people use microwave sintering. In these cases, you get more sintering, lesser grain growth. So these are some of the things that can be looked at. You can also use pressure assisted sintering, but the problem is that for pressure application, you need some kind of a die, which again will put a restriction in your shape that you can form. So I will not talk about this any further. The reason is this I have probably wrongly put it. Yeah. So sometimes okay, let me skip this part. And one of the techniques that people have started talking nowadays, it has become more and more publications are coming in this topic, is without application of any load, you can use electrical voltage to a threshold where you can sinter these products at a very fast rate in a few seconds. Zirconia was sintered at 850 degrees C using this process in about 10 seconds and close to 100% density. That means greater than 99% density. So this has become very popular. Can we adopt this into our AM manufacturing? That's the question. So if somebody can do that, the AM manufacturing will have some respite in terms of sintering of the products. Now, other issues with the AM is, like, for example, this is selective laser. This here the example is from selective laser melting or selective laser sintering. This is zirconia part, and you can see the surface, these pores. You can see these pores. At the surface, these pores. And see, the surface is not good. You can see that here. Surface is not that good. The reason is, again, it gets sintered. Like I have powder bed. If I have a laser which sinters it, and then I raster it, sinter it, it goes. Sometimes the powder gets sintered. I put another layer, and because of that, sometimes in between there is unsintered part, unsintered area, which is loose powder, which is not sintered well sometimes. Because of that, when you process it, it results into, and these large pores will never close. Very small pores, if you sinter it, can close, but larger pores will not close, and that's what is shown here. This is laser sintered, this one, and you can see the cumulative volume of the pore versus the equivalent radius. See, greater than 0.1 micron, you have pores here. So much, 40% to about 80, so about 20%, and then you have 1 micron pores, about 10%. These are not going to close, so that will remain with your product, and it's very difficult to get very dense products in these cases. And another problem with the SLM is the residual stress. You are always building layers, and top layers are getting more exposure to heat, and the bottom layers are a little bit cooler, so it develops a stress in your product. Here's another example of avionic pod camera, which was produced by 3DP. Now, after getting the product, the reason is, again, the 3DP, what you use is a binder to make the product from a powder bed. So you get a lot of adhered powders to the product, and also the surface is not at all good. So you need to mash in a lot of things, before you can get a green finished product. Green finished product that has to be sintered later. So this is the green finished product, and they had to remove, in order to get this complex shape, they had to remove about 80% of the actually printed part, and they get these walls and these features by machining it to that extent, or removing that much of a powder, scraping out that much of a powder. And then when it was sintered, you can see how much change happened in the size. So this is a picture actually taken from a German company which produces these products. So large parts are still a big challenge, and this is not very large. You can see this is just 200 millimeters. So that means this hole is about 20 centimeters, 20 centimeters, and so this size is hardly about 40 centimeters in diameter, and yet it is so challenging. And it is almost like 80% machining means you are not doing additive manufacturing. So the outlook I will just say, and then I will take up the questions. The most important problem is to achieve very good packing density to start with, and then you should do rheological studies. That's very, and then you have to, the powders has to be optimized. The shape and powder size distribution has to be optimized, and rheological studies has to be done. The most processing technology everyone talks about nowadays for ceramics is slurry based, where you have done good rheological study and have optimized it, the slurry, and then use photolithography. The last product I have showed you was from photolithography. And traditional powder processing, classical powder processing technologies, which are used for extrusion and other things, those know-how has to be integrated to the additive manufacturing to get good products as far as the ceramics is concerned. And getting monolithic product of ceramic, large part, is still a challenge. Okay, and a lot of research groups have started working on it. With these notes, I would like to say thank you. Now I am open for the questions.
Good evening, Professor.
Yeah.
Good evening, Professor. This is Dr. Balakrishnan from Kumarasamy College, Karur, Tamil Nadu.
Yeah.
So, in continuation with my earlier questions, the cracking susceptibility between layers, how to control this between layers?
Okay. So there are two. I have showed you one in case of stereolithography. I showed you one way to really calculate how much CD can be. So if you have decent overlap, if you are using SLM or SLS, the fusion overlap, you need to ensure that. That's an important part. If you have some loose parts in between layers, it will certainly will not be stronger.
Yes.
And also one more point is you need to preheat as far as ceramics is concerned. Sometimes the reason is you need to remove the stresses between the layer. So preheating is sometimes good during printing as well. And if you have a finished product,
at interpass preheating. Interpass preheating, no. One layer to other layer.
See the whole printed object. So do the printing in a warm environment. So that reduces. Sometimes they use a secondary laser can be used to raster it from the lateral sides, to make it more uniform while you are building the layer. And one more point I would like to put from my side would be when you have just made it, before you go for final sintering, you add a stress relief sintering at lower temperature.
Okay. Sir, so is there any?
If we apply this combination, I guess it might be okay.
Okay, sir. Thank you for your nice explanation. And is there any soft interlayer may be introduced in between layers so that we can compact for?
Yes. It is possible. Generally, people do it in case of laminated lamination processing or laminated object processing. You can use interlayers. In case of ceramics, they use sometimes a zirconia alumina layer. So the problem with the lamella is that if you are deliberately adding it as a functional part, or it is a functional layer, then that's better. But sometimes what happens is that the interlayer becomes a weakness because more layers you add, more interfaces you add. So that has to, you have to think about your product, what exactly you want to add and what application you have.
And Professor, is there any hardness reduction after deposition of all layers? Since it is deposited layer by layer, that is repeated heating and cooling would come, no?
Yeah, so
across the
I did
thickness
not get
direction.
your question. Okay.
Is there any hardness reduction after all layer deposition?
Yeah, so hardness is when you talk about layer, each layer will have its own hardness depending upon your material, what material you have on that layer. And hardness is very local property. What I would say is strength wise, if you apply loading to open the layers, that will not be stronger. If you apply loading where the layers are all elongated together, that will be stronger. But hardness will depend on the material itself.
No, my question is actually, since it is depositing layer by layer, that means it is continuously heating and cooling. The layer is heating and cooled continuously, successively. That is the reason why I am asking this question actually.
So in ceramics, generally, you do not see hardness reduction because of annealing. They are inherently hard materials generally. If you are talking about see, the interlayer will always be weaker unless you are fusing the layers.
Yes, exactly.
And if you fuse the layers, then again the fusion layer and the non-unfused layer will again have an interlayer. Sometimes that sublayer is also weaker.
Professor, what is the highest thickness it was produced until now by this additive manufacturing of ceramic component? Maybe in any quantity, can you define this much height it was deposited by?
Okay, generally several millimeters and centimeters monolithic products are made. One product I showed you was from a German company, but it looks bigger, but actually it is made up of thin walls of several a few centimeters. Some company might have made the larger products, but I'm not aware of it.
Thank you, Professor. And you mentioned the residual stress. It can be reduced in between heating and cooling. That is during the residual stress relieving during the manufacturing itself. But my question is, what is the effect of residual stress expected from the additive manufactured ceramic components during its service?
See, if you have residual stress, then what happens is, if let's say, for example, if the residual stress is tensile, and your strength of material or material can sustain 100 MPa root meter, 100 MPa or 200 MPa. So now your residual stress is about 10 MPa. So that's reduction in your strength. That stress is already in there in the material, and if you apply additional loading, then it's going to crack. Also, in ceramics, they are very fragile in the sense that they have very low fracture toughness. So if the stresses are there, it will relieve itself by increasing the length of the crack and make it more prone to the fracture.
Easily getting fracture. But if we wanted to additive manufactured ceramics to offer for better properties, it could be deposited with low dense component. Am I right, Professor? Low dense.
Yes, porous products are something people are now pushing. Actually, that's what I showed you. The hydroxyapatite or the biomaterials, it is more successful because they inherently require porosity.
Thank you, Professor. Thank you so much. Thank you so much.